Yeah, I'm live on Facebook.
Okay, can someone check that we are live on YouTube?
Yeah, live on YouTube as well.
Good morning. It's 11 o'clock on a Sunday morning, and it's time for Chai and Why, our summer specials. Had there been no COVID, we would of course have met at Ruparel College and have a lot of fun meeting in person and trying out various things. Unfortunately, we have to continue this series online. Today, we enter the world of mathematics, looking at shapes, surfaces, geometry, topology. And to tell us about all this, we have Professor Maharaj from DIFR, who is a geometer and one of the best persons who can explain the most complex concepts to a very wide audience. A few years back, he had the entire Prithvi Cafe with him trying out drawing things and calculating things. I don't know what he has in store for us today, but I'm sure it's exciting. So over to you, Mahan. But before we do that, just remember that we can't look at you. So the only way we can communicate with you is via chat. So please put your questions in the chat on YouTube, Facebook, or if you're on Zoom, in the comments or question and answers, and we will try and take them as we go along. So over to you, Mahan.
Yeah, thanks a lot, Arnab. Thanks a lot. You've raised expectations, and I hope I live up to them. Anyway, so a few years back at Prithvi Theatre, there was a lot of fun, and definitely it's much more entertaining and much more interesting when we learn this stuff together. Because this Zoom medium, I mean, has this tendency of being sort of one-way traffic, and that's not. Yeah, that's, well, this is the best we can do for the time being. But in order to have a better feel of some kind of a live interaction, so feel free to ask your questions on chat. And I think Ulas and Arnab and others, there is already this live chat here. So I think I can see some of these. Yeah, so it says, please put your questions and comments here or in the Q&A box. So please feel free to shoot questions. I'll be aware that you have asked questions. This is the problem. Okay, yeah. All right. So feel free to ask your questions on chat, and somebody is going to throw them here. And yeah, okay. So there's going to be one little intermediate step, but that's all. Okay, so what I work on is there. It's shapes and geometry is what we are interested in. And there were a bunch of questions even before this thing started, which is very exciting. Basically asking what's the raison d'etre? I mean, why on earth should one care about shapes? Why on earth should one care about surfaces? Why on earth should one care about geometry? And since the first half of the talk is actually geared towards addressing that particular question, we can start the talk as an answer to some of the questions that you have already posed. So here's the simple thing. When we look around us, I mean, as human beings, our how do we see an opaque object in front of us? We don't see the 3 dimensions. It's our brain that computes and tells us that there is a 3rd dimension. What we actually see is the surface of the object, right? So if you have something that's opaque, through which light does not pass, it's the surface of the object that one is looking at. Yeah? And the shapes in the title refers exactly to this. That's all. So in some very grandiose terms, what are shapes? All visual information. That's where it is. That's where it is all starting. Yeah. And why would one want to study? Well, again, by being members of this crazy species called Homo sapiens, whenever we see something, we would like to make a map of it inside our brains. That map, if it's sufficiently structured, is called understanding. So we can't help it, being a member of a species that likes to understand whatever information comes in. So this particular talk is going to be about visual information and how we process it in terms of formal mathematical structures. That's the point. Okay. So when we look around us, there's a vast range of shapes that we see. Okay, bewildering multitude. So here is a shape of the Earth, right? Viewed from far, just a globe, a sphere. Well, that could be thought of as boring. So here is something more interesting, and I'm sure this guy does not have a name. Yeah, so there's just some shape. And let's see some more. Now here there's another couple of things. You have these two spheres which look as if there's some tar connecting two globes, and then once you stretch them out, you get this picture on the right. So these are some other shapes. So what we have done here is just collected a bunch of shapes. Here is another more exotic looking thing. That little golden band, tube that goes all the way around, is essentially what is called a knot in three-dimensional space. And then there is some green thing that is spanning that knot. Okay. So this is just some range of shapes that we see when we look around us. Now the point is, how are we going to organize all this visual information? That's the point. So how are we going to organize all this information so that when we see a new thing, we'll be able to say, oh, okay, this is actually very similar to this other thing that we've seen before. So how do we organize this? And so the principle of organization of this visual information is a certain kind of formal structure. So two problems arise. First, we've said visual information, that's too vague. Yeah. So we want to make this notion of visual information, naive visual information, precise. And we said that, look, what we see are surfaces of objects around us, three-dimensional objects and their surfaces. And what we want to do is make this particular notion precise so that we can manipulate that notion on paper and pen, or on a laptop or on a computer. Essentially, we want a notion which can be communicated between us as species. See, if I want to say that this is a sphere, I can't bring you the Earth and say, okay, look, this is the Earth, right? So what we did was we had a pictorial representation. I said, look, this is a sphere. This is supposed to be the shape of the Earth. That's the kind of representation that we want. Yeah? Essentially, a representation in our brain which we put on paper. So first we need to make precise what we are talking about. So what are surfaces? That's one of the things that is necessary in order to even address this problem of how to organize visual information, how to organize this information of surfaces that we see around us. First question. And essentially, we've already mentioned the answer. As we said that, look, the 3 dimensions is something that our brain tells us in order to give a certain depth, but what we actually see is the surface of the object, which means what? Which means we don't see the 3rd dimension, we just see the surface, which is locally a 2-dimensional object, which means if you bring your eye very close to the surface that you're looking at, it will look like a little flat plane. Yeah. Essentially like the floor on which we are standing. And if you look at the wall and you bring your eye very close, it will look like just a piece of flat paper. Yeah. So the way a flat paper looks and the surface of a wall looks, from very close up, it doesn't look very different. Yeah, that's the point. Okay, so that's the structure that we are going to abstract out. So we started with this naive notion of all visual information. We zoomed in a little into that particular notion and came up with this idea of surfaces of objects. Now we are trying to make that notion, surfaces of objects, a little more precise. And essentially we come up with a slightly more precise thing, which basically says that it is locally two-dimensional. Now, how is that? Have you come across this locally two-dimensional notion before? Indeed, you have. When you look at an atlas, at an atlas of maps, yeah, what are you really looking at? When you're looking at a screen and you're looking at a picture of this country, that country, political, in terms of what kind of vegetation grows where, etc., etc. What are you really looking at? Heat profiles on the Earth. What are you looking at? You're looking at a map of the Earth on a flat screen. What has that done? It has taken the surface of the Earth. It has put some part of it flat on a piece of paper. There's a map between the two. So essentially what you're doing is the map is representing the surface of the Earth. This map that you see here is clearly a two-dimensional gadget. It's not a three-dimensional. So the surface of the Earth, locally, we are assuming, we are doing this without sort of spelling it out. We are taking the surface of the Earth, mapping it by some kind of a map which preserves all the information to something that is locally two-dimensional example. And really, this is one instance of the kind of thing that we want to study. So starting again, let me just go back. Starting with all visual information, we made that more precise to think of locally two-dimensional objects, to think of surfaces of objects. And then we made that even more precise, which is coming closer and closer to the more abstract domain of mathematics. And we are really looking at locally two-dimensional objects. So essentially we want to sort of define fairly precisely what are the objects we are playing with. So the player in the game, the chief player in the game, has now been reasonably well identified. The other thing that we want to know is, what does organization of all this information mean? So information here now is being replaced by locally two-dimensional objects. This is the information that we want to understand. Well, what does understand mean? And we said that we want to organize this information. And so what we really want to replace this word organized by is the word classify. So essentially, we started off by saying we want to organize all visual information. Now the word organize has been replaced by classify. Information has been replaced by locally two-dimensional objects. And the problem we started off with has been made a little more precise. And now what we want to understand are, the problem that is the title of this talk is classify all locally two-dimensional objects. Yeah. In more human terms, this was organize all visual information. And the same thing in slightly more precise terms is saying classify all locally two-dimensional objects. Okay, so now I think we have come from our sort of naive interaction with the world to a slightly more abstract world which interpolates with mathematics. Okay, so that's the problem that we are trying to address. Fine. So now let's try to probe this thing a little further. So now the thing is we replace the word organize by classify. And now what we want is, what does classification mean in this context? See, this is the way almost all of science progresses, right? Say in biology, you have this vast range of animals and plants around us. And what does it mean to understand this natural world we live in? basically say, okay, so look, this plant and that plant, they are the same, and this plant and that plant are different. Or this animal and that plant, this animal and that animal are the same, and this animal and that animal are different. Well, which means what? Which means we are trying to put them in various dockets, right? And then we are saying, okay, so these species, their behavior don't change drastically. That's what classification is supposed to mean. So in mathematical terms, again, so we do the same thing in mathematics as a science. Now, what are we trying to do? What we are doing is, first, we want an exhaustive list. In other words, in this particular case, all locally two-dimensional objects must be represented by something on this list. That's one. Second is that the list should not have redundant elements, which means any two members of the list should represent distinct things. So which means we have a list where there is no confusion, which means two fellows inside the list are not the same. Second, it exhausts the entire collection of possibilities. That's what we are after. First, an exhaustive list with no redundant elements. Second, now we need a method. Yeah, so these are our dockets. It's like having a bunch of files or folders, actually not files, folders. You have a bunch of folders on your machine, on your laptop or your desktop. And now you have a new file that comes in. What you do is take that file and put it in the folder. You know precisely which folder it belongs to. You take that file and put it in that folder. In other words, suppose I have a list of a bunch of animals, and now I see a new animal. So the list that I have is animal 1, 2, 3, 4, 5, 6, etc., etc. See a new animal X, and I'll be able to say which of the animals, maybe 4 it is. And then I take that animal X and basically say that, look, this picture belongs to this folder 4. That's what we want. Yeah. So we want first an exhaustive list with no redundant elements. Second, if we see a new two-dimensional object, new surface, new piece of visual information, we'll be able to say exactly which member in the list is something that is the same as that particular new two-dimensional beast, new locally two-dimensional surface. More formally, the second thing, this method, we want to say, so what we want is we should be able to essentially, so when we want to say pick a new fellow and put it in this docket, we basically are saying that, look, there is a method in our head which tells us that this new guy and this, whatever the collection of guys are there in this docket 4, that's the same. So there needs to be a method to say that these two fellows are the same, which means what? There has to be such and such characteristics. Yeah. So we'll have some list of characteristics, and we'll say, look, these characteristics determines this particular docket 4 uniquely amongst this entire collection of dockets. 1. Second, this new guy satisfies exactly those characteristics. That's the meaning of classification. Yeah. So this is a general scientific method, and we are applying it to the class of surfaces. Okay, locally two-dimensional gadgets. All right. So now let's go back and try to understand, with this sort of spiel that we've been talking about, what locally two-dimensional really means. And why did we say that the Earth, the surface of the Earth, is locally two-dimensional? Okay. Before I go on, are there any questions there on which people would?
Yeah, so if you have a question, please do put it either in the chat, on Facebook, anything on Facebook, Divya, and or on YouTube. Let me just check YouTube. I do not see any questions as such. Lots of good mornings.
So
and hellos.
One question on FB is that something related to you're saying that the Earth surface is basically locally 2D, but what about the poles? Is there some specific thing?
Fantastic. Okay, so I think these questions are sort of
Yeah,
cues for you
sorry.
to go on. So
Just to interrupt, you just repeat the question because the person on the FB will not hear me. So if you just repeat the question.
yeah, sure. So I think the question that is being asked is, okay, so the surface of the Earth, I said, was locally two-dimensional. What about the poles? Yeah. And here's the thing. So look at this particular surface of the Earth. Yeah. So there are these two poles. Yeah. There's a top pole and there's the North Pole and the South Pole. And here in this particular picture, I mean, I think the questions are actually very well designed for me to sort of go on. I mean, it is really a cue. We right now have a picture of the Earth and the North Pole. So look at this picture here, right here. What does it look like? It looks like a point, and you have all the longitudes coming in and the latitudes there around that as concentric circles. So you take the North Pole and you put it flat. What does it look like? You're looking straight down at the North Pole. That's a point. And from there, there are these radial lines. So all the longitudes have now become radial lines if you push it flat. Yeah. And the latitudes are now concentric circles. What is that? See, that's exactly the radial coordinates we learn in school. There is an R direction, the radial direction, and there's a theta direction, right? There's an angle direction and the radial direction, which means what? It looks exactly like, again, a flat piece of paper, but the flat piece of paper has a chart which is given by radial lines going outward and concentric circles around it. So if you instead of drawing the X and Y coordinates on a flat piece of paper, if you draw a point and then radial lines going out and circles concentric orthogonal to it, perpendicular to it, you're going to get exactly a picture of the surface of the Earth around the North Pole, similarly around the South. Hopefully that addresses the question. There is another way to address this problem also. So here is a picture of the Earth. Now suppose I take this picture and rotate it, yeah, so that the North Pole has now moved to the equator. And here's the thing, as a shape, it's we as human beings who have said, look, that fellow that's up is north, that fellow that's down is south. What if we decided to call northeast and southwest? Yeah. Essentially, what happens is that then the pole will be replaced by a point on the equator, and the opposite point will become the other pole. And then the North Pole will have charts exactly like these little square rectangles that we have done on the surface of the Earth. So which means that if instead of looking at an atlas where you remove the North Pole and remove the South Pole and flatten it out, if you remove one point on the equator and its opposite point and flatten out the Earth, again, you are going to get a different kind of cockeyed charts. Yeah. But there are still going to be charts. That's going to be another way of saying that, look, even at the North Pole, the Earth is locally two-dimensional. Okay. So these are two ways. Whichever is you feel more comfortable with is fine. Basically says that the surface of the Earth everywhere, even at the poles, is locally two-dimensional. So the surface of the Earth, so this is what we are trying to say here. We have drawn this grid of latitudes and longitudes so that each little piece there is like a little piece on a graph paper. Yeah? So it's a little square or a little rectangle, which you can actually draw more or less faithfully on a flat piece of paper. And it's these little rectangles, where my cursor in the shape of a hand is marking out. These little shapes here, those are that's really what captures this locally two-dimensional nature of the surface of the Earth. Okay.
Mahan, there are a couple of questions, and I think right now we are looking at a sphere, ideal sphere as Earth. We're not worrying about mountains and lakes and all those things. So I think that is something we should clarify. And
Absolutely.
someone asks, but isn't the pole one dimension? And I don't understand. I mean, the pole is still a point on the surface of the Earth, so you can put some,
Yeah.
it can be anywhere on the. It's just a
Yeah,
point
exactly.
on the sphere.
Exactly.
There's another question which says, at some point you said scale.
Yeah. So Arnab, let me interrupt you for a moment.
Yeah.
So here, what are we really looking at? A pole or any point is a point on the Earth. The point is not what we are calling locally two-dimensional. If you look at a little neighborhood of that point, so for example, all of us are sitting somewhere. Just look at the floor that we are sitting, we are standing on or sitting on. Yeah? That floor typically has tiles. So those tiles mark out the locally two-dimensional nature of the surface of the Earth. Yeah. Even if we are on a very steep mountain and somebody has built a little house there, the floor is going to locally look like a flat thing. So it's just that the chart is very small in comparison to the shape of to the huge size of the Earth, but that's how it's going to look. If you have a tent, say suppose you have somebody who's who lives on the North Pole, bang on the North Pole, and he's built a little tent there. What will the floor of the tent look like? It will look like a flat piece of white sheet. There'll be ice presumably, but it's just going to look like a flat white square or rectangle or flat white floor. Yeah. So that's the point of saying that, look, the surface of the Earth, wherever you look, locally it looks like a two-dimensional. Okay, go ahead, Arnab. Yeah.
Okay, the other question, which let me just see, is, somebody has asked a question: is scale two-dimensional or three-dimensional? I don't quite understand. Yeah, think about scale somewhere. I mean, I don't know whether they mean a scale like in a ruler, or did you talk about scaling something? I don't know.
Yeah, so no, I guess
I'm not sure. Priyanka, if you can explain your question.
Can they be unmuted or?
Yeah, I can ask. Yeah, Priyanka Kamath, do you want to ask what your question is? Yeah.
Yeah, go ahead.
Go ahead.
I have a scale with me, so actually I am thinking that is scale 2D, like it has a base on its side, so I think it is 3D, but it is.
Yeah, you're absolutely right. It is 3D. Absolutely right, Priyanka. It is 3D. Yeah, go ahead. You want to say something more?
But it doesn't look like the other 3D objects.
So are you talking about a scale like this, Priyanka?
Yes.
Okay.
All right. Wonderful. Okay, very good. Thank you for that question. So yeah, so here is a suggestion. Is your scale a plastic scale or a wooden scale?
Glass one.
Oh, glass one. Yeah. So here is it does not matter. See, I think the part of the reason why it might be confusing is because it is plastic or glass, because it's transparent. So you remember right at the beginning, I said that when you have opaque stuff, which do not, things which do not allow light to pass through, then you can actually see the surface well. So here is a suggestion. You take your plastic scale and say wrap it with a piece of paper, stick it tight on the scale. Yeah, you can do that.
Yes.
Okay, good. So after you've wrapped a piece of paper tightly around your scale, then that piece of paper is not going to allow light to come through your scale, right? Then what you do is, now you can forget the scale inside, and then the little piece of the paper that you wrapped around it locally has taken on the shape of the scale. Yes?
Yes.
So what does it mean to say that the surface of the scale is two-dimensional? Now you remove the scale and unopen the paper. The paper had the shape of the scale to start off with, but locally, what does it look like? Paper, the surface of the paper is something two-dimensional. That's what you have wrapped around your solid object, the scale. So the piece of paper is two-dimensional. That's all that what I'm saying really boils down to that in the specific case that you're talking about. Does that clarify your question, Priyanka?
Yes.
Okay, excellent. So we were saying this stuff about the surface of the Earth, and we also mentioned that the poles are locally two-dimensional. Here is something else, which actually makes even more precise. Somebody called Dhairya Rakesh Jain has raised his hand. So yeah, we'll come. So Arnav will ask the questions a little later, but let me clarify this particular issue right now, and then we'll come back to your question. Okay.
So maybe I will request people type out your questions, and we will read them out to Mahan. And if Mahan asks you to then unmute and ask something, then we will allow you to talk. Okay. So for now, I would say just go ahead and type out your question. And Dhairya, do you have a quick question to ask? You can ask, since you are unmuted anyway. Go ahead.
So is a water droplet 2D or 3D? Because when it falls, it's like in 3D, and when it comes on, it just goes 2D.
Yeah, I understand. But again, you are asking me about questions, about examples which are transparent. I had mentioned right at the beginning that you should think of opaque objects, objects which do not allow light to pass through them. So think of a droplet of tar, black solid tar. So now that's a little ball of tar. A little ball of tar, you look at the surface, that is locally two-dimensional. It's exactly like the surface of a sphere. It's exactly like the surface of the Earth, except that it is a much smaller thing. Which means what? Okay, fine. As human beings, we look at things at a scale of, say, meters or centimeters. But now look at a scale of, say, something like millimeters or even smaller. And the surface is just going to look exactly like the surface of the Earth, flat, two-dimensional.
So what if you take a droplet of mercury?
Everything, droplets of everything will look like, locally, the surface is going to look like two-dimensional. It does not matter whether it's mercury or tar or anything. Okay, so let me now get back to this particular thing, which is a nice, interesting shape. It's essentially the shape of a rabbit. It ought to remind you of these balloon animals that are occasionally sold at crossings, at traffic lights. So you have a balloon, and then some part of the balloon is tied up with some piece of string, and some ear is built out of that, etc., etc. And so here we have built out of maybe some fabric or maybe out of some flexible material like plastic or rubber. You have a shape of a rabbit here. What does it mean? So we are trying to explain this idea, which is what these questions were about. What does it mean to say that surfaces are locally two-dimensional? We'll come back to the classification problem a little later, but we are again trying to address this question about what it means to be locally two-dimensional. And I think the real point behind all your questions that you asked over the last couple of minutes is basically, what does locally two-dimensional really mean? And this picture is supposed to illustrate that. So you take, what is happening? You think of the surface of the rabbit being made out of some fabric. And here in this corner, you have a little square, which takes a little patch of the surface of the rabbit and puts it flat. And what has happened, if you look at these black areas, they are like lines, they are drawn diagonally, but it's exactly like X and Y coordinates on a graph paper, except that they have been tilted by some angle. So it's like some bunch of lines parallel to each other in one direction and a bunch of lines perpendicular to them in another direction. So essentially what we really mean when we say that a surface of an object is two-dimensional, it means you come very close, look at a little patch there, cut that out, put it flat on a piece of paper, and this is what it's going to look like. Essentially, it means that very close up, everything looks like a flat piece of paper on which you can put X and Y coordinates, on which you can put lines which are perpendicular to each other. That's really all that it means, yeah? Which means, what is a piece of paper with this graph thing? That is something called the real line. Real line gives you numbers. So here you have real lines giving you numbers in two directions, X and Y coordinates. That's what it is about. Okay. So this is what two-dimensional stuff is. So here in this particular slide, I'll give you a very precise notion. It's not necessary that you understand all the words, but what it means is what we have already talked about. Surface is also, by mathematicians, these are also called two manifolds. Manifold just means locally it looks like Euclidean space, the space we live in, or the flat plane on which we walk. So locally it's something that is very familiar to us. That's what it means. So a surface, formally it's also called a two-manifold, yeah? It's something that is locally two-dimensional. So now what is the meaning? How do we say is locally two-dimensional? It means that there is a map, right? So just as on the, you took a piece of the surface of the earth and you drew it on a chart paper, on a map in an atlas. So what happened is that map, every point in that map is supposed to represent a point on the earth, and this is supposed to be a faithful representation. Every point corresponds to a unique point, and so if you in principle, if you understand the map perfectly, then you will be able to understand perfectly what the part of the world part of the earth that it represents. So this exact correspondence has a special name in mathematics. It is called homomorphism. And this R2 is what? What is it? It's just these X and Y coordinates on this flat piece of paper. Informally, all that we are saying is that a surface is something that is locally two-dimensional, and locally two-dimensional means you will be able to represent points and little neighborhood of them by charts and say graph paper on a flat notebook. Yeah? So far, what have we done? So far, what we have done is looked at only the surface of the earth, and even this rabbit we'll be saying a little later from a certain notion, which allows us to bend and twist things without tearing, without cutting. It's really not very different from the sphere. Question is, are there any other examples? Yes, yes.
Mahan, just two questions.
Yeah.
So, are all objects locally two-dimensional? So, if I come close to any object, if I come very, very, very close, is it always going to be two-dimensional? So that's one question by, unfortunately, anonymous attendee.
Yeah.
And
lovely question.
There is another question on YouTube. Asked by Parthasarthi Mukhopadhyay, who was asking, is it possible to have a surface which is not locally two-dimensional? Or are every, I think they're related. So no. Is every surface, if I come close enough?
Yeah. So here is the thing. Firstly, the way we have talked about surfaces are necessarily locally two-dimensional. That's, in a certain sense, that's almost a tautology, because that's what we are, what we are saying is when we see the surface of an opaque object, just the surface of the opaque object, it is two-dimensional. Yeah, so it's either a tautology if you're saying that a surface is by definition something that is locally two-dimensional, or in terms of visual information, then if you have something opaque, then you're seeing really only the surface of it, so it's two-dimensional. That's part of the question. But if you make the question a little more general, and ask whether is every object necessarily locally two-dimensional, then certainly the answer is no. This earth we live in, yeah. So don't think only of the flow. We ourselves are three-dimensional creatures, right? So there is a third dimension, there's a depth, which we are not taking into consideration when we are looking only on the surface. So if you add this extra dimension, say a cube, a solid cube, you can't see inside it. But not being able to see inside it does not mean that the third dimension does not exist. Yeah? So what are we doing here? We are confining, we are saying ahead of time, we want to confine our attention only to visual information. And that visual information is necessarily two-dimensional, and then there are maps. Yeah. But if you say that, no, we are not going to confine ourselves to visual information only, but also to extra information which our brain tells us, namely this depth, which we infer, then you can add that dimension and you have this three-dimensional space in which we live in. I mean, none of us thinks that we are living in a two-dimensional world, right? We think normally that we are moving in a three-dimensional world and we can move in three directions. We can jump off the floor, right? So that's going up in the third direction. We can walk in any of these two directions, or we can jump up and down. So there are these three directions in which we can move. Aeroplanes fly, rockets fly. So that means there is a third dimension that we are assuming in our thinking. The point is, when we see, only if we confine ourselves to visual information without this extra piece of inference, then we are ignoring this extra third dimension in our experience. When we are saying that we want to only confine ourselves to locally two-dimensional surfaces, locally two-dimensional objects. Yeah. So first, surfaces by definition are just surfaces of opaque objects. Those are locally two-dimensional. But as normal human beings, we have this notion of a third dimension, length, breadth, height, in our thinking. So when you deal with objects, you can assume, I mean, all buildings, when you design a building, you don't just design the shape of this. So it's, if you look at it just from outside, locally it looks two-dimensional, but you can have a third dimension inside which it bends. So this two-dimensional gadget, the surface of the sphere, is sitting inside a larger space which is three-dimensional. Okay. Hopefully that addresses. Arnav, should I clarify anything further?
No, I think that's good for now. I think it's good
okay. That's good for now, and we can come back to these questions later on.
Yeah.
The point is, so far we have been looking at things which really, I mean, the only example that we have been thinking of is really the surface of the earth, the sphere, and things which are small deformations of that, like the surface of a rabbit. Question is, are there other examples? And here, surely there is. So this is a surface of a donut or a bicycle tube. It has a formal mathematical name. This is called a torus. Yeah. The surface of the earth is called a sphere. This is called a torus. So, but this also, here also you see that there are charts. There are these little rectangles, and so if you come very close, you're going to look at only this locally two-dimensional thing, and that's the surface of the bicycle tube. So the surface is like two dimensions. So there are other things. There are other examples. This is a genuinely different example. I mean, you cannot twist and turn. So now we are going to come up with a more precise notion of equivalence. You cannot twist and turn the surface of the torus without tearing it and convert it to a sphere. This is a fact. Okay. And so now we come back to this other notion. See, first, so far what have we done? We have tried to explicate the two problems, right? One is, what is a surface? And so now we have some understanding, locally two-dimensional. It has some formal precise notion, homomorphic to R2, locally homomorphic to R2, which means that you can put charts. Now we have to come back to this notion of when two of these gadgets are the same. Yeah. And the same is given by this extra word homeomorphic. I'll say the formal thing and then I'll try to explain in intuitive terms what this word means. So we need a precise notion of equivalence. That's why we are using this word. This means basically that from the first to the second, there is a continuous way of mapping the first to the second, and there's a way of coming back continuously. Yeah? So from the first to the second, there's a continuous guide. From the second to the first, there is another continuous guide. Yeah, which brings everything back. What is the intuitive idea? The intuitive idea of saying when are two objects the same? And this is the notion of sameness which defines a field of mathematics called topology. Basically means that you can deform one continuously to the other without tearing, without gluing. Yeah? This is the intuitive idea. So for example, here is an example of a homeomorphism. So you start with this dumbbell with 3 bells. Yeah. So there's a sphere in the middle and there are these 2 gadgets at the on the 2 sides. Then what you do, you start deforming. So the middle fellow starts becoming slimmer and slimmer. And finally, the 2 things at the 2 ends, those have now become more or less uniform. And here you have something which is just an oblong. And finally, you have something which is essentially like a sphere. So you started off with something like a dumbbell. Yeah. You're allowing a continuous deformation without tearing, without gluing new stuff in. And finally, you have deformed this original gadget to essentially a sphere. So what does that? So the formal mathematical way to say it is that the first object you started off with is homeomorphic to a sphere. So this is a terminology, this is a precise word, which basically says that you can deform the first down to the second, and if you retrace your path, you can deform the second one back to the first. Here is another example. How are you going to do it in a grid? So here you have say something which is like a lemon, but with lots of crinkles, say like the surface of the earth, with lots of mountains and valleys. And then you start deforming it. You start making it smoother and smoother. And finally, you have a nice, round, smooth lemon. Yeah. So essentially, this is, if you want to run this deformation on the surface of the earth, you will be able to deform it without too much effort into a nice round sphere. Yeah. So this is what it means. So this is what we mean when we say that the surface of the earth is a sphere. Is means that you can continuously deform without cutting, without tearing. Yeah. And the formal mathematical word for it is homeomorphic. Good. So now what we have, we know what surfaces are locally 2-dimensional objects. We know what same means. It means one can be deformed to the other without tearing or cutting. So now we can actually address this problem. Classify all visual information has now become a precise notion of classify all surfaces where 2 fellows are the same when they are homeomorphic, which means one can be deformed to the other. And recall what we wanted. We wanted a list that was exhaustive and did not have repetitions. Yeah, that's what we want. Plus a method of saying if you pick one gadget up, you will be able to say which guy in this list it is. So I'll give you 3 examples. And they look very different. Yeah. So you have these 3 little, it's like a pretzel. Yeah. The second one, the rings are sort of arranged in a line. Yeah. Stacked one on top of the other. And here it's like a teapot with 3 handles. Yeah. There's nowhere you can pour things from. The point is that these 3 gadgets are actually the same. How do you go from the first to the second? You essentially assume that this stuff is made of plasticine. Yeah. So stretch this out and just push this right side into the middle, and you'll come to the second. Yeah. Again, if you pull the middle fellow out, you're going to come back to the first one. So the first and the second are the same. How about the third one? Well, you have this fat stuff in the middle. You just make it a little smaller, then it will look like a small little thing with 3 handles coming out of it. And that looks very similar to this. The stuff in the middle is that little flat. If you blow up this, fatten up the stuff that is there in the middle, it will look like a big sphere, and there'll be these 3 handles, and that's this one. Yeah. So essentially, though these pictures look very different, they can be continuously deformed one to the other, and so they are homeomorphic. So they represent the same object in this scheme of classification. Okay, so that's an illustration. Now we'll come to the statement. So what is this? This last picture is basically a 3-handled teapot. Formally in mathematics, what does it say? It says that, okay, this stuff in the middle, it looks like a sphere, like the surface of the earth. So the surface of the earth is a sphere, but it has 0 handles, no handles attached to it. If you attach just one handle, you're going to get back the torus, this picture. This is the same as a sphere with a single handle. Your teacup, yeah, the surface of a teacup, yeah, the cup from which you drink your tea or coffee with one handle. That's exactly this torus, yeah. And this is a gadget with 3 handles. The point is, so we started off with the sphere, which has 0 handles, a torus, which is a sphere with 1 handle attached, and somehow we did not draw any pictures where there are 2 handles. Yeah, so assume that, so you have these big vases which have these 2 handles which you hold, and say one of these victory cups. Yeah, so that's a cup which has 2 handles attached to it. Yeah, so that's like a sphere with 2 handles. This is an example with 3 handles. And so you can go on, right? You can keep attaching handles one after the other. So you started with 0, that's the sphere, that's the surface of the earth. 1, which is the torus. 2, which is this cup that is given after a tournament. Then this is a cup, this is a sphere with 3 handles, and you can have 4, 5, 6, 7, 8, 9. For every so 0 is the sphere, and then for every positive integer, you can have a sphere with n handles. So that's a whole collection of, that's a list, right? That's a list. Why is it a list? It's basically got a correspondence with 0, 1, 2, 3, 4, 5, 6, etc. That's a list, right? What does it represent? How many handles you've attached to your sphere. And here is the statement of the theorem. Forget the rest of the stuff. Roughly what this is saying is that every surface, every closed surface that you see around you is really a sphere with n handles for some n belonging to 0, 1, 2, 3, 4. Which means what? Go back to our classification problem. Essentially what it says is that you wanted an exhaustive list. And what is that exhaustive list? As I've said, it's a sphere with 0 handles, 1 handle, 2 handles, 3 handles, 4 handles, 5 handles. That's your infinite list. No 2 of them are the same. Second, it is exhaustive in the sense that given any locally 2-dimensional thing that you see, you can deform it into exactly one of these gadgets. That's the point of this theorem. Formally, what it says, any closed, there is one extra word which I would like to draw your attention to, orientable, and I'll explain in the next couple of slides what orientable means. Any closed orientable surface, closed means it's contained in some bounded amount of space. Yeah. Any closed orientable surface is homeomorphic to, which means it can be continuously deformed to, a sphere with n handles for some non-negative integer n. This is our classification theorem. Okay. So this problem has been solved. It was solved in the 19th century, towards the end of the 19th century. But we needed this extra hypothesis of orientability. What is orientability? And I'll explain it in the next couple of slides. Orientable just means it has well-defined sides globally. So here is an example of something that is,
Okay, so maybe while you were deforming, there's a
Yes.
question from Orijit who says homeomorphic does not mean it has the same surface area. It need not have the same surface area when you do this
Exactly.
thing.
Absolutely true. So the surface of the Earth and the surface of a map, yeah. Say 1 square kilometer is represented by in a map by 1 square millimeter location, right? So certainly the area need not be the same. Certainly that's true. Lengths are not necessarily the same. You are allowed to twist and turn. Yeah.
Okay, there's another question which I'm not quite sure I get, but I'll ask the question. Scott Knox asks, why are we defining surfaces with 4 points and not 3? Did you define a surface with 4 points at some point? I don't know.
No, I don't.
I think you said you had X and Y on it.
X and Y coordinates.
Coordinates, yeah.
Yeah, so locally X and Y coordinates. So
I don't think you need 4 points to define a surface, right?
Yeah, no, we don't.
Okay. Yeah, there are other questions which I think you will either come to. People are jumping ahead, or or we'll ask them at the end. One of them.
Okay. So the next, go ahead. Yes, go ahead.
No, go ahead. I think the others will take them.
So the thing is, there's the question that orientability basically means proper sides. So here I have drawn a picture. This is what is called the Mobius strip. So these ants are actually supposed to indicate the direction that points out from the surface. So you start with this ant at the top, yeah, and think of this, the middle legs as a normal direction that is pointing out from the surface. So it is here, the ant is on the top, which basically says that there's a perpendicular to the surface pointing upward. Now you follow this ant around this Mobius strip all the way around. And once you come back to this other ant. So if you follow this ant, the ant is traveling without any problem in its life. Yeah, it's just traveling continuously without jumping anywhere. But once it has traveled all the way around, what has happened is that it's come to this other ant, which is a little behind it, which has the perpendicular pointing downwards. Which means what? Which means you started off with a point where the perpendicular was going outward. Now you traveled some path on your surface, and then you came back to the point you started off with, but now the perpendicular is pointing in the opposite direction. In other words, the ant cannot say that, oh, this is the right direction and that's the wrong direction. Which means if you follow the ant around this Mobius strip, the direction reverses itself. In other words, a Mobius strip does not have two distinct, well-defined sides. This not having two distinct, well-defined sides is what is called orientable. Yeah. So something which does not have it, like the Mobius strip, is called non-orientable. Here is another example, and it's essentially like this is what is called a Klein bottle. I won't go into it. It's closely related to the Mobius strip that we drew. Here's another example. I'm just drawing this just to give you examples. And this picture is a bit of a cheat because this surface has had to intersect itself here, and the previous one in this little round thing here. Yeah, you're not allowed to intersect yourself in a surface. Yeah. Okay. So these are examples. So these are things that we are not including in our classification theorem of sphere with n handles. The point is these don't really create too much of a problem. That classification theorem can also be extended to non-orientable surfaces, but it's not very enlightening. So that's why we've excluded them. Okay, finally, so this was shapes. So we discussed shapes so far. And somebody asked, well, what about lengths? And what about the other, so more finer features? And here is the thing, in order to understand, so now we've done, basically what we did was we took a very coarse kind of docket, and what we want to do, or folder, now what we want to do is inside folders, we want to create subfolders. Yeah. So basically, what one is saying is that, say the surface of the rabbit, Yeah, so imagine the rabbit being a balloon animal and its ears are all tied up with strings. And if we remove those strings, it pops up into a nice round balloon. Yeah. So it can be continuously deformed to the balloon. So the surface of the rabbit that we saw some time back is the same as a sphere. But clearly, when we see it, we say that no, the surface of the rabbit is not the same as a nice round sphere. Yeah, it is. It is the same up to this cockeyed notion that mathematicians have come up with, that you are allowed to continuously deform, and that defines some kind of equivalence. And according to that equivalence, a sphere and the surface of a rabbit are the same. So that field is called rubber sheet geometry. So if all shapes were made out of a rubber sheet and you are allowed to twist without cutting and without pasting, then that's a field that would be called topology. Yes, okay. So they're topologically the same. That's the more precise way of saying it. Meaning that one can be deformed to the other. But how about the original geometry? We've actually ignored that. We've forgotten a piece of information when we are allowing things to deform continuously from one to the other. And now what we are asking is, what is the information that we are forgetting when we are allowing these two things to be continuously deformed from one to the other? And here the thing is, a rabbit is a sphere topologically, but not geometrically. So what is geometry? That has this, okay, so one kind of geometry that has this extra notion called curvature in it. And what is curvature? So here is the thing. Roughly, how would one think of curvature? Say, essentially, let us look at all these solids here. This actually links up to what we had done in Prithvi. These pictures that we have here are what are called Platonic solids. Yeah. And the curvature you can think of as concentrated at the vertices of these solids. And it determines how pointy it is, how sharp the point is. One thing that you can easily think of is that the tip of this gadget here, say a four-sided die where all the four sides are equilateral triangles. So that's called a tetrahedron. All of you have seen a cube. Yeah, a cube it has 6 sides, all of which are squares. This is an octahedron, which means it's built out of 8 equilateral triangles. Yeah, so it's like a pyramid with a square base and 2 such pyramids glued together, where all faces are equilateral triangles. This guy is a little more interesting. This is called a dodecahedron. It's got 12 faces. Every face is a pentagon. And finally, this, which is the most complicated, this is called an icosahedron. It's got 20 faces. So the dodecahedron has had 12 faces, each of which was a pentagon. This has 20 faces, each of which is an equilateral triangle. And here is a prettier picture of the same thing made of crystal or glass. So these are examples of what are called Platonic solids. That's not very important. The point is that these are like polyhedra, and the vertices, the points here at the tips, these are sharp tips. And how sharp can be measured. And this measure of sharpness is what we can call curvature. Okay, this is a very naive, intuitive notion, and it is exactly this which can be generalized to the notion of curvature which we compute. So what is this notion of curvature? Note that all the surfaces, yeah, so if you assume that this is not made of wood but made of some kind of rubbery material, then you can pump it full of air and it's all going to become nice and round. It's as if you've taken a round sphere and you put a grid on it and you're not allowing it to blow up into its normal nice round shape. So if you pump air in, all the surfaces are actually going to look like spheres. So if you allow them to deform, you're going to get back the sphere. But the curvatures at the vertices are different. The pointier the vertex, the more curvature that it has. Yeah. So how are we going to measure? So we want numbers. Yeah. We want to say, no, not in these vague terms that, look, this fellow is more curved, this fellow is sharper, but how much sharper? We want to associate precise numbers to these. And so this little letter here is called chi. Yeah? This letter here is called chi, and it is supposed to be at the curvature concentrated at a vertex. Now, what is something that is not curved at all? So something that's completely flat is not curved. Yeah. So the surface of a table has no curvature at all. That's our sort of starting point. So we want to define a zero. Yeah. So zero means the surface of the, say, the flat surface has no curvature, which means how are you going to measure that? If you take a point and you measure the total angle around that point, how much does it come to? It comes to 360 degrees, or 2 times pi. Yeah. The difference of the total angle around the vertex from this 2 pi is, so that is a nice number that measures the difference between the curvature concentrated at a vertex and the flat thing. So this angle defect is a placeholder for curvature. Okay. So we define it this way. What is it? 2 pi, the total angle around a vertex, and then look at the sum of the angles of the various faces that are coming and hitting the vertex V. That is these theta i's, the angles. This angle defect is called the curvature concentrated at the vertex V. And this is a measure. This is a clear number. What is it doing? It is measuring the difference from the flat Euclidean plane. So now let's do this for the nice interesting case dodecahedron. Yeah. And we'll use a little bit of elementary school geometry to compute this. So let us take this dodecahedron. Okay. So it has 12 faces. It has how many vertices? 1, 2, 3, 4, 5. First round, there are 5. Second round, there are another. Yeah, so this is 1, 2, 3, 4, 5. And then there's a third level, which also has 5. And then finally, there's another one there, which is 5. So essentially 5 into 4, 20 vertices are there. But at all the vertices, this is a very regular object. So all the vertices can be interchanged. So essentially, we'll really need to do the computation of this angle defect, the total angle defect. If we do the angle defect computation at one point, that's going to give us the angle defect at every other point. Yeah? This particular case, for this particular regular dodecahedron. So what is the angle defect, say, at this particular vertex, at one of the vertices? Okay. How are you going to do that? We are going to compute. So what is it? It's 3 times the internal angle of a pentagon. What is the total angle around a vertex? You have these 3 pentagons coming and hitting. Each pentagon is regular, 5 sides. So that's some Euclidean pentagon. It has some internal angle, and 3 times the internal angle is the total angle around this vertex. Subtract that off from 2 times pi, and you're going to get the angle defect at a vertex. So here we do the computation. So what is the angle at a vertex? Yeah. Okay. We are going to use a simple fact from Euclidean geometry. The sum of the exterior angles of any flat Euclidean polygon, convex, is 2 times pi. So there are how many sides? 5 of them. So the exterior angle at every vertex, if you put it flat on a plane, is 2 times pi divided by 5. So what will be the interior angle? It's pi minus 2 pi by 5, which is what? It's 3 pi by 5. So this is the angle here, interior angle of every pentagon is 3 times 180 divided by 5, which is 180 degrees. So every pentagon, the interior angle is 108 degrees. That's what this means. Theta I is 3 pi by 5. Good. Then what is the angle defect? It is 3 of them. The total angle is 3 pi by 5 plus 3 pi by 5 plus 3 pi by 5. 3 of them. plus 9 pi by 5. Subtract it off from 2 pi. What do you get? You get pi by 5. So the angle defect at every vertex of the dodecahedron is pi by 5. 180 divided by 5, 36 degrees worth of positive curvature is there at every single vertex of the dodecahedron, of the regular dodecahedron. So what is the total angle defect? Total angle defect, as we said, there are 20 vertices. So if you sum the total amount of angular defect is 20 times pi by 5, which is 4 pi, Now let's try to do the same computation. I've done a sort of a slightly involved computation involving the dodecahedron. Let's go back to the earlier pictures and try to do the same computation, say for the cube. Yeah. A cube has how many vertices? 4 and 4, 8. Good. One piece of information, 8 vertices. Now look at a single vertex. What is the total angle at that vertex? 90 degrees plus 90 degrees plus 90 degrees. Right? There are 3 squares. Each square, the internal angle is 90 degrees. So 90 degrees plus 90 degrees plus 90 degrees. So what is the angle defect? It is, so that's pi by 2 plus pi by 2 plus pi by 2. That's 3 pi by 2 is the total angle. Angle defect is 2 pi minus this sum, which is 2 pi minus 3 pi by 2. That means positive curvature worth of pi by 2, worth of 90 degrees at every vertex. Pi by 2 curvature concentrated at a vertex. How many vertices in all? 8. So 8 times pi by 2. What is the total angle defect? 4 times pi. Same as what we got for the dodecahedron. Good. Let's do it for the tetrahedron. What are the internal angles? 60 degrees, 60 degrees, 60 degrees, and there are 3 faces, 4 vertices. So total angle at a vertex is 60 degree plus 60 degree plus 60 degree, that's pi, 180 degrees. Angle defect 2 pi minus pi, that's pi. How many vertices? 4. So total angle defect is 4 times pi, which is the same thing as that something that we got from the cube, and something that we got from the dodecahedron. So there seems to be a bit of black magic going on. Yeah. Here we seem to have sort of thrown out a lot of, we thought that we were going to recapture all this information, but then we sum all these angle defects to capture local information, and then we started summing. And when we started summing, we are still getting 4 times pi. That means that the sum is the same. Well, here is a point, and this is a theorem. It's called the Gauss-Bonnet theorem in this particular version. If you look at any cellulation, I don't care what way you divide your sphere. Here we have done regular things. You look at the angle defect and sum over vertices, you're always going to get 4 times pi. Yeah. Now, where does this 4 times pi come from? Okay. And to elucidate that, I will not prove this. It's nice to look at the other surfaces that we looked on in the topology part of the top, where you were allowed to deform. And here is the thing. What was our collection of surfaces? Go back to that part. It was a sphere with n handles. So if you have a sphere with 0 handles and you sum angle defects, you're going to get 4 times pi. If you do a cellulation or decomposition into polyhedra of a sphere now with n handles attached, n handles, this n is here. What you're going to get, and you look at the angle defects and you sum, you're always going to get some expression which depends on n. If n is 0, then you have the sphere. So that's minus 2 pi times minus 2, which is 4 pi, which is what we got. This is the Gauss-Bonnet theorem. It basically says that it does not, this total amount of curvature. So essentially, what were we doing? Yeah, locally the curvatures might be different. On site, on a flat plane inside one of these faces, the angle around it is 0. But at the vertices, there is curvature concentrated. The total amount of curvature, if you sum over the whole surface, then that depends exactly on the number of handles. In other words, mathematicians say This is a topological invariant. It does not matter on the precise local geometry of the surface. Local geometry differs, but you take the average of the geometry, you integrate out the geometry, you sum up the angle defects, and you get back something that depends only on the topology, only on the number of handles you have attached. Okay? So this second part, this particular theorem essentially says roughly that if you want to carry a slogan back from here, it is that average of geometry is topology. Okay? Or geometry, that's if you take a sum over all possible things, then what you get at the output as an output is just something that is topological, that is invariant under deformation. Okay? So I think I'll stop here. Thank you.
Okay, all right. So, of course, we have lots of questions, and I'm sure people will keep asking more questions as the talk is over now. And let me take a few from both. Let me first try Facebook because I can't see Facebook. So, Divya Shankar, are there any questions on Facebook? And then I'll move to the questions on Zoom and
one question is how will you describe 2D surface of an ant sitting on top of a needle?
So, can you repeat that question? Very interesting question. Yeah,
so
go ahead.
How would you describe the
local 2D surface you were talking? How will you define that?
Of an ant sitting on a tip of a needle.
Right.
Yeah. Okay. Very good. So how about we go to something slightly less exotic than an ant on a needle? Suppose as human beings, we are on the top of, say, on the top floor or on the roof of, say, some high-rise building, yeah, or some huge tower. When we look down, then we'll still see a flat floor, right? So that will still look like a locally two-dimensional gadget. The point is, the tip of a needle is very sharp, and if you want to really look at it, if you want to look at it locally, ant is not good enough. So you need a much smaller creature. Say, for example, think of an amoeba, yeah. So or maybe something even smaller, yeah. Then when it is crawling on the tip of the needle, what will it do? It will still be looking as if it's crawling on some floor, right? So this illusion is being created because we can't. So if you imagine, forget the ant. If I am standing on the top of, say, a thin stick trying to balance myself, I won't think of that the tip of that stick as two-dimensional. But that's a problem with the resolution of my eyes. Yeah. If you look at it at a finer scale, again, it's going to be locally two-dimensional. So this is really a question of point of view, perspective. Yeah.
Yeah, there is no other question, but several messages like very good presentations and enjoyed the presentation thoroughly this time.
Okay, I'm glad.
So yeah. let's get back to some questions. So now let me go to YouTube where I had told people please wait, we will get these questions later. Okay, yes. So let me we'll come back to.
There's a lovely question here.
Yeah,
we'll have to come back to Priyanka.
We'll come back to Priyanka on Zoom, but since you can't see the YouTube, let me read out the YouTube questions to you.
Yeah.
So in physics and maths, we often talk about invariants. Is homeomorphism some kind of invariance? Asked by Chinmay.
Yes, it is. So it is. So this is. It would be good to know which level
you're at.
This.
Yeah, Chinmay, which level? Chinmay Mishra, if you're still there on YouTube, you can just write which level you're at. We'll come back to it. There is a question from Ram Sheshadri, which says that can there be negative number of handles similar to negative numbers?
No. So for this, For two-dimensional surfaces, the answer is no.
Okay, two-dimensional answer
So
is
for
no.
two-dimensional surfaces, the answer is no. However, negative numbers do appear, and so here it's number of handles you are attaching. Yeah, so you can't attach. You can't add a negative number of handles. However, there are examples in topology where some negative number does make sense, and yeah, but that will take us. Right now the kind of examples that I'm having in mind will require a little more sophisticated terminology to develop. Let me say this much, that yes, there are, not in two dimensions, but if you try to sort of decorate this two-dimensional thing with some extra information, yeah, then the notions of negative numbers do come in and play an important role.
Okay, so let's go back to Zoom now. So Priyanka had this question. I think you've seen it as well.
Yeah.
Are there any more dimensions?
Fantastic question.
Like 4D
yes.
or 5D, etc.
Absolutely. Absolutely. There are any number of, you let your imagination run, and however much it might run, you have that many dimensions. See, the point is, so now let me, with apologies to other members of the audience, yeah, mathematicians have a sort of a weird, part of their worldview is a little skewed, in the sense that if we come up with certain things and it does not fit reality, whatever reality means, our usual response is so much the worse for reality. We are not going to quit our maths, right? So Priyanka, if your imagination allows 4D, 5D, fantastic. Yes, this is absolutely right. It's and the curious thing, and this is sort of what a great physicist called Wigner once called the unreasonable effectiveness of mathematics, which is, if there is some mathematical structure that you find, yeah, in, say, for example, higher dimensions, you're asking about 4D and 5D. If you had just stepped up one more dimension and said 6D, I would have been, yeah. So there are structures in 6 dimensions which have become increasingly relevant to theoretical physics over the last 30, 40 years. That's, and actually it has come back to mathematics as something that we ought to be looking at. So yes, certainly if there are, you see, what is it? What are 3D? You're just putting coordinates, right? X, Y, and Z. Well, as many letters as you can just throw in. And if English runs out of alphabet, just put X1, X2, X3, X4. Numbers don't run out. So just put coordinates X, Y, Z, that's 3D, X, Y, Z, W, that's 4D. So any space which requires 4 coordinates to determine a point precisely is 4D. 5 coordinates, 5D. That's all. So you can run on. Of course, there are other dimensions, except that they are there in our mind. Yeah. So these are abstractions.
Okay. And Arush had a question. Can a 3D object then be homeomorphic to a 2D object or some other dimension object?
Fantastic question. Fantastic question. The answer is no. The answer is no. But this requires work. Yeah? This is a theorem that you cannot deform. This is called Brouwer's invariance of domain, yeah? Which basically says this number of dimensions is a topological invariant. So that's a theorem, but it requires it will require more work to prove it. Great question. Great question.
Okay. Then we have Shayantan Sharkar asking, can we define a homeomorphism between a torus and 2 intertwined Mobius strip?
No. So a torus so Mobius strip is non-orientable. No orientable surface is homeomorphic to a non-orientable.
Okay, and which now brings me to the question. A question on. Actually, the question is retracted, but I think it's worth explaining. Arjav had a question about, can you please explain what is orientable again?
Okay, that's a good question.
Actually, Mahan, if you want, if it makes it easier, I don't know if it will make it easier. we could also show people. I have a little strip of paper. I can
Yeah, great. Go ahead.
So by the way, if you want a little homework problem to do, here's a little strip of paper. Just tear a strip of paper. And now normally when you would stick the paper, you would stick it like this to make a little loop. Okay. This would be a normal loop of paper. The Mobius strip, the picture which he had the ants crawling over, you can make a Mobius strip at home. When you stick it, just twist this once and stick it together. Okay. Twist this once and stick it together. You will get an object which looks like this. Okay, make this little strip, just tear a strip of paper, newspaper, anything, and just twist it once before sticking it. You get what is called a Mobius strip. And now you can take a pencil and just start marking the Mobius strip from one side. You know, if you're not an ant, but you have a pencil, just go around and you will find that when you come back, you will have marked both sides of the strip. But then, you know, the strip has only one side effectively. There's no two sides of this. You can do more fun things. You can take this Mobius strip, take a scissor, and wherever you had drawn that line, cut the strip. And I'm not going to tell you what's going to happen. You can have more fun. This question somebody asked, why twist it once? Why not twist it twice? Try it out. So instead of twisting it once and stick, you know, you can, this is a strip with 0 twists. I can twist it once and stick it. I'll get a Mobius strip. I can twist it one more time and stick it. I get some more complicated thing. Try these out. Try it out. Yeah. See what happens when you cut it in the middle. See what happens when you draw a line on it. This is all fun stuff you can do. All you need is a strip of paper, and I think you'll have a lot of fun with these things. And you know, okay, that's just a little aside.
Arnab, let me just add a little bit to this.
Sure.
I mean, yeah, okay. So this particular kind of experimental stuff that Arnab is telling you about, this is with the Mobius strip. But let me tell you one thing: when we were PhD students, the person who sort of started the modern version of some particular kind of geometry called Bill Thurston, we were all second year PhD students and we were feeling very foolish, but he essentially asked us at that stage to essentially cut paper and paste it in order to get a real feel for hyperbolic geometry. I mean, so that's one particular kind of geometry. This is a bunch of all grad students sitting together and like young people, we were actually just doing this by hand to get a feel for that. So yeah, I mean, essentially even sort of top level mathematicians do this. I mean, this is the way, the only way you can really learn to get a real tactile feel of what this is about is by doing this kind of hands-on stuff.
Okay, so Chinmay, who had asked a question about, what was it, about invariance, I think. Is homeomorphic some kind of an invariance? He says he's a final year master's student in applied mathematics.
Okay. So what was his question? Can you just say that again?
In physics and maths we study invariance. Is homeomorphism some kind of invariance?
Yeah, it is. It is. It's an equivalence relation. It basically says that. So essentially, it's an equivalence relation. So which means what? Which means that if two fellows are A is homomorphic to B, B is homomorphic to C, then A is homomorphic to C. If A is homomorphic to B, then B is homomorphic to A, and A is certainly homomorphic to itself. So it's an equivalence relation. And what we have been discussing here is that the homomorphism equivalence classes are in one-to-one correspondence with these numbers 0, 1, 2, 3. That's a one-line summary of this in this language.
Okay. Right. Let's see other questions. Okay, there's a question saying why is the minus there, but I don't know where. So Ramasing, if you can specify where is the minus sign you're worried about, we'll look at it. There's a question about, I think chromatic number of a surface depends on the number of handles. I don't know what is a chromatic number, but if this question makes sense to you.
Chromatic number is of graphs. So what do you really mean by chromatic number of surfaces? Surface is a continuous object. What is the chromatic number of the real line?
Okay,
I don't know. I don't know what one is.
All right, let's see. Are there any other things? So, Priyanka has another question which says, why don't we see the other dimensioned objects daily?
So Priyanka, here is a suggestion. See it in your mind's eye. Yeah. That's the only place. See, we can't see it because we belong to the stupid species called Homo sapiens. That's the answer. Yeah. What can we do? It's a pity. But the thing is, okay, so here is that's sort, at least in part, a joke. But I mean, yeah, that's what defines us as a species. We can't do that. But you can actually certainly imagine. Here is a suggestion. How would you if so there is a little book which you might like. It's by somebody called Edwin Abbott. It's called Flat Land. Yeah. So suppose we were actually not as, we were even more unlucky than human beings are, and we lived in a two-dimensional world. How would we imagine 3 dimensions if we were two-dimensional creatures? That's the problem that this particular little book, it's not a very big book. It's by Edwin Abbott. It's called Flat Land.
I'll put that in the chat. I'll just put that in the YouTube comments as well. Flatland, a romance of many dimensions.
Yes,
I think that's the name of the book.
Yes. And I would strongly encourage those of us who are asking these questions about 4D, 3D, etc., strongly suggest that people look at that book. And those who have an orientation towards mathematics can look at this book by, it's called, never mind. For now, maybe let us stick to Flatland. Yeah. And those who are oriented towards physics can certainly look at this beautiful book by Brian Greene called The Elegant Universe. Yeah.
Okay. Let's see. Are there any more questions? Does anybody want to put up their hand and ask a question? We can allow you to do that. Just raise your hand and I will then unmute you. And
hang on. So there are some other questions.
Okay, there are some more questions coming in. Arush Murali, yes. Two new questions. Could a locally flat surface be non-differentiable everywhere?
Yes, answer is yes.
Okay.
But I don't want to get into it. The answer is certainly yes.
And
locally, okay, hang on. Just a moment. What exactly do you mean by locally flat surface? Flat should not be the thing. Can a surface be non-differentiable everywhere? Yeah, answer is yes. Yeah. Locally two-dimensional. Flat means curvature. Yeah. So flat, we should not get in. Flat really means you are already differentiating. So flat means the way to define curvature formally is through differentiation. So it does not really make sense. But if you are just talking about something which is a surface, yes, the answer is yes, it does. It can be on. Can a self-intersecting surface? Again, a self-intersecting, if something is self-intersecting, it is not a surface in this sense, in the sense that we've been talking about. Yeah. So, but yeah, flat, locally flat, if by that you mean curvature 0, the answer is yes. Certainly true, possible.
Okay.
So Priyanka has her hand up.
Yeah, so Priyanka, you may unmute and ask your question, please.
Are there many such objects which we have not seen in the outer galaxies or universe? Like
No. So they're not in the outer galaxies, but they're in the outer galaxies of your mind. Yeah. So think of them. Yeah. You can just let your imagination run, draw things, and start trying to think of how you would think of extra dimensions. Yeah.
Okay. Dhairya Rakesh Jain, do you want to ask a question?
Yes, sir.
Yeah, go ahead.
Go ahead.
Why are there so many strange names for such complicated objects like a dodecahedron?
Dodecahedron. Why is it called dodecahedron? So what is deca? This is, do you think 10 is a strange name? Or 12 is a strange name for a number?
No, sir.
No. So these are names that Greeks came up with. So deca is just, Greeks would say 10. Instead of we say 10, Greeks say Dekha. Yeah. In Hindi, we would say das. Nobody thinks of it as strange, right? So it's just that these words came from Greece. So those were the people who actually initiated the study of geometry. That's why we continue to call them by those names. Dodeca means 12. Okay, that's all.
So was Euclid the father of geometry?
Geometry has been around for a very long time. Euclid summarized some of it, but geometry has been in existence even from before Euclid.
So did even the cavemen know how to do all these things? Like not with all these numbers and stuff, like imagining things which were crazy.
Of course. So, of course, I mean, the very fact that they could paint. Human beings have an intuitive understanding of geometry. It's basically visual information and processing. That's all that there is. I mean, geometry is just a way of formalizing it and putting it on paper, and we discuss it in class. But it's something, say, for example, the musical sense. You don't have to be a musician to have a musical sense. Every person has. So the sense of geometry is there with all of us. Yeah?
Okay.
I mean,
anyone?
yeah.
No, it's fine. Go ahead. I don't want to interrupt you.
No, that's fine. That's fine.
Okay. So no, it's we are past 12:30 already, but it's been going on really well.
Yeah.
Anyone else with a question? Anyone else would like to ask a question?
No, there is another question.
Yes,
Anonymous attendee. Sir, can we never reach at the same point for any non-orientable surface while traveling? No. This is a different issue. This is connected. If a surface is connected, you can always reach one point from another. Okay? So do that experiment that Arnav was telling you about of going round a Mobius strip. And what will happen, what you will see is that you go around and you come back to the same point, but your pen is on the opposite side. Here is the other thing. You carry on that thing one more time and see what you get. Yeah. Go once around the Mobius strip till you come to the opposite side, and then go around again and see what happens. This is actually important. This is going to it's going to give you a sense of what the Mobius strip is about.
So
Yeah.
Are there any shapes like which were named after some space objects?
Are there any? So for example, what do you mean?
Like any shape?
What do you mean? Yeah, named after what?
Constellations of things.
No. I'm not aware. There might be, but I'm not aware.
Okay, I think we've had an excellent session. Thanks so much, Mahan, for taking.
Thank you, Arnav. I enjoyed it thoroughly.
To interact with everybody of all backgrounds, and I hope all of you have got some idea of a connection between geometry, where we typically measure angles and things like this, and this field of topology, which is almost telling you whether an object has holes in it or not, or handles, and whether you can squish it and do something to it. And the fact that all these things are related and all these things are, mathematics has so many different branches, so many different areas, which are all exciting, all interesting, and many of them, the beauty of it is you can do things in your imagination, you can do things beyond what is actually limited by the reality that we see over here, table, paper, pen, whatever it is. So I hope you enjoyed this. Do tune in. 2 weeks from now, our next session, which is going to be the last of our summer sessions, is going to move from, Mahan, can you stop sharing perhaps?
Yeah.
We'll move from mathematics and go back to biology this time. We haven't had a biology session in summer, so we're going to do a biology session, and it's going to be on mutations. So you must have heard about mutations. At least you've heard that the SARS-CoV-2 virus is mutating and they're getting all these new things. So what is this mutation all about? How does something mutate? How do you study it? And we will also hopefully do some experiments, some very simple experiments. So don't forget, join us 2 weeks from now again on Chai and Wai, Sunday, 11 o'clock. And till then, please stay safe. If you're going, out with any place, please remember to wear your masks and keep safe distance wherever you are. Until then, stay safe, stay healthy. Thanks a lot for watching Chai and Why. You can always see the other episodes if you've missed on YouTube, on our YouTube channel. Thank you, and thanks for joining. Bye for now.